we are going to work through several examples of verifying trigonometric identities. I have at the top here three just things that will help us think through these. So as you read them, choose the more complicated side. What we're going to do is we're going to choose the more complicated side, and we're going to try to simplify it to look like the less complicated side. Number two, we're going to use identities. So we have most of our identities here on the right, the ones that we're going to use anyway in this worksheet. We can use identities. We can definitely use factoring. We'll be using that quite a bit. Sometimes we'll use distributing. Sometimes we'll be having to get common denominators and add fractions. There might be some other things that I haven't listed here, but we're going to simplify the more complicated side to try to look like the less complicated side. Number three, it says sometimes it's helpful to think about what the less complicated side is actually equal to. So maybe another form of it, or how could we get to the less complicated side? And then one thing I didn't mention here, sometimes if we're stuck, we can change everything to sine and cosine, and we can do that using reciprocal identities and quotient identities, which we can put any trig ratio we want into something that deals with sine and cosine. All right, so we're going to get to it. We'll try to talk through why these things are true as we work through them. So this first one, cosine cubed plus sine squared times cosine is equal to cosine. Now, oftentimes I neglect to mention the variable. I will try to mention it, but sometimes I do forget. So what we can notice here is the left side is definitely the more complicated side. And we can use identities, factoring, distributing, adding fractions to try to make it look like the right side, which is just cosine of theta. And so what I notice here is that I have a cosine in both. Now I have a cosine in the first one and a cosine cube in the first and cosine in the second, but I can factor out a cosine of theta out of both terms, and that leaves me with cosine squared theta plus sine squared theta equals, and I actually don't even usually rewrite cosine theta because we're going to keep that the same throughout. And why did we do that? Well, that was factoring. So I'm just going to put over here that we factored out a cosine. All right, now, as we look through identities, do we notice any identities that would help us get to just cosine? Well, before I do that, I notice that right here, it says cosine. So cosine times what is equal to cosine? Well, times 1. So is it true that cosine squared plus sine squared is equal to 1? Well, it is. Whenever we see squareds, trigonometric ratio squareds, it is often helpful to look at the Pythagorean identities. So down on the bottom right here, we have the Pythagorean identities. And we notice here, sine squared plus cosine squared is equal to 1. So we can take out our sine squared plus cosine squared, and we can make that 1. So we still have cosine here times 1 equals cosine, and that was using a Pythagorean identity. You're going to want to be familiar with all of our identities, that one especially, that sine squared plus cosine squared is equal to 1. And then lastly, we could just write cosine of theta is equal to, and this right side is cosine theta. So we verified that identity. In fact, we could have probably stopped here and not written the 1 and just said cosine theta equals cosine theta. Number 3, secant theta times sine theta equals tangent theta. I would say the left side is the more complicated side. And another thing to notice is the left side is still just one term. There's no addition or subtraction. So really we're hoping that this is just equal to tangent theta. And one thing I mentioned before, like this number 3, sometimes it's helpful to think about what is the less complicated side equal to. Well, we do know that tangent from our quotient identity is equal to sine of theta over cosine of theta. And so maybe we can get to that. And that's actually exactly what happens. We already have a sine theta, so we realize that, well, secant can be written as 1 over cosine theta. So we have 1 over cosine theta times sine theta still equals that right side. Why can we write that? Well, we can write that because that was a reciprocal identity. Change secant to 1 over cosine. Now we know that sine over cosine, or 1 over cosine times sine over cosine is just sine over cosine. Might have just said that wrong. And then from our quotient identity, we have sine of theta over cosine of theta is equal to tangent theta. So our last step, we have tangent of theta is equal to tangent of theta. So go back, this we just multiplied fractions. Probably could have skipped that step and just gone to right to tangent, and this was a quotient identity that we used. Now, just to mention or remind this, we could have written tangent theta and just kept writing tangent theta all the way down here because we wanted the left side to look like the right side. However, you don't need to just keep writing it. You can just put the equal sign and assume that's going to be the same thing. All right, the last one we can squeeze in here, secant squared minus 1 over tangent theta is equal to tangent theta. Well, once again, I would definitely say the left side is the more complicated side. I'm noticing over here that we have a secant squared. So as mentioned before, if you have a squared, you might want to consider the Pythagorean identities. Secant squared, and especially if it is with 1, which I should have mentioned before, if there's a 1 involved, a squared and a 1. So what I'm going to do is I see a secant squared over here on the bottom right, as I'm highlighting, and a 1. And so what we can do here is we can think of this in another form, and we can do this often. So we can perform algebra to this expression right here, and we can subtract 1 from both sides, and we would get tangent squared is secant squared theta minus 1. And so what we see there is we can take out a secant squared theta and just put tangent squared. So using a Pythagorean identity, we can say on the top here we have tangent squared theta. Denominator is still the same. We're hoping that equals tangent theta, and you're probably already seeing it. And we used a Pythagorean identity here. And another hint for that, just to remind you, is if you see something squared, especially if that square is with a 1. And now we can simply simplify. So we have tangent theta equals tangent theta. And we just reduced or canceled, simplified